In the depths of space, 10 billion light years from where we stand, there exists something that should not be possible. When scientists first calculated its properties, they checked their mathematics again and again, certain they had made an error. They had not. What they had found was a cosmic monster that would rewrite our understanding of what nature can create. This is a journey to the edge of cosmic possibility, to a place where gravity becomes so intense that it tears apart the very fabric of space and time. We will travel backwards through time itself, racing across billions of light years to witness something from when the universe was young, when galaxies were still forming, when the cosmos was far more violent than today. The object is called TON 618. At its heart lies a black hole containing 66 billion times the mass of our Sun, compressed into a region whose boundary would extend 40 times farther than Pluto's orbit, if placed where our Sun sits. It shines with the luminosity of 140 trillion suns, making it one of the brightest objects in the universe, despite the 10 billion years its light has traveled to reach us. When this light began its journey, Earth did not exist. The Sun had not yet formed. The universe was barely a quarter of its current age. Let us begin. That band of light stretching across our night sky is the Milky Way, our home galaxy containing hundreds of billions of stars. Somewhere within lies Sagittarius A's star, a supermassive black hole containing 4 million solar masses that anchors our entire galaxy's rotation. By any normal standard, it is enormous. But what we seek is 16,000 times more massive. Our destination is not in this galaxy, not even close. To reach it, we must leave behind every star visible to the naked eye, push beyond the local group of galaxies, beyond the Virgo supercluster, beyond everything familiar. We must break the cosmic speed limit itself. As we accelerate past light speed in this thought experiment, the Milky Way shrinks behind us. Its spiral structure becomes clear, revealing graceful curved arms, dark dust lanes, bright star-forming regions scattered throughout the disk. Soon other galaxies appear. The large and small Magellanic Clouds, our satellite galaxies, then Andromeda, our nearest large spiral neighbor containing perhaps 1 trillion stars, approaching us for a collision in 4 billion years. We push outward. More galaxies emerge, dozens, hundreds, thousands. Each contains hundreds of billions of stars. Each star might have planets. Each planet might harbor life. Yet we have never detected a signal from another civilization. Perhaps we are alone. Or perhaps the universe is so vast that civilizations simply cannot find each other across the cosmic void. Now we enter true intergalactic space, regions so empty you could travel millions of light years without encountering a single star. The temperature here is just above absolute zero, warmed only by the faint afterglow of the Big Bang itself. But darkness does not last. Points of light begin to emerge, scattered at first, then multiplying until they fill every direction. Galaxies, thousands upon thousands. These galaxies are not randomly distributed, but organized into vast cosmic webs, sheets, and filaments separated by enormous voids. This is the large-scale structure of the universe, carved by gravity over billions of years as matter flowed along invisible rivers of dark matter, clustering into dense knots and leaving vast, empty spaces between. As we travel farther, looking deeper into cosmic time, the galaxies change character. Nearby galaxies are mostly mature systems with orderly rotation and reduced star formation. But as we push back in time, galaxies become younger, more irregular, more active. We see more vigorous star formation, more evidence of mergers and interactions. This makes sense. When we look at distant objects, we see them not as they are now, but as they were when their light left them. Light from a galaxy 10 billion light-years away shows us that galaxy as it existed 10 billion years ago. We are literally watching cosmic history unfold. Ahead, one point of light grows brighter than the rest. This is no ordinary galaxy. This is a quasar, a beacon shining across cosmic distances with power beyond imagination. When these objects were first discovered in the early 1960s, astronomers thought they were seeing strange stars in our own galaxy. They appeared as points of light, showing no structure even in powerful telescopes. But when astronomers analyzed their spectra, measuring the characteristic fingerprints of different elements, they found something impossible. The spectral lines were shifted dramatically toward longer, redder wavelengths, indicating these objects were receding at tremendous velocities, often 10% or more of light speed. According to Hubble's law relating velocity to distance in an expanding universe, this meant these objects were billions of light-years away. If visible at such distances, they had to be incredibly luminous, more luminous than entire galaxies containing hundreds of billions of stars. Yet they appeared as points, suggesting all this energy came from regions no larger than our solar system. The energy density was higher than anything previously encountered. The answer, which became clear through the 1960s and 70s, was supermassive black holes consuming enormous quantities of matter. As material spirals inward through accretion disks, heating through friction and magnetic interactions, it radiates vast amounts of energy before crossing the event horizon. This particular quasar, designated TON 618, was first catalogued at the Tonantzintla Observatory in Mexico in 1957. For decades it remained largely ignored, one more blue point among thousands in a stellar survey. But as technology improved, astronomers realized this was exceptional. The black hole, at its heart, was not just massive, but ultramassive, one of the largest ever discovered. As we approach, the quasar resolves from a point to a disk, then to a vast churning maelstrom. We are now close enough to see the components that make this object shine so brilliantly across the cosmos. Surrounding the black hole extends an accretion disk spanning thousands of astronomical units, a swirling vortex of doomed matter. This disk has distinct regions with dramatically different properties. In the outermost regions, far from the black hole's strongest influence, the disk resembles a slowly rotating gas cloud. Temperatures are relatively cool, a few thousand degrees comparable to red dwarf surfaces. Material orbits at a few hundred kilometers per second. The gas is still mostly neutral, not yet ionized. Moving inward, conditions intensify. Gravitational pull strengthens and orbital velocities increase. At a few hundred astronomical units from the center, material orbits at thousands of kilometers per second. Friction becomes intense as different parts of the disk orbit at different speeds. Faster inner material rubs against slower outer material, converting orbital kinetic energy into heat. temperatures climb to hundreds of thousands of degrees, then millions. The gas becomes fully ionized plasma, free electrons, and bare atomic nuclei. This plasma is threaded with magnetic field lines generated by charged particle motion and amplified by dynamo processes. These fields are crucial. They transport angular momentum outward through the disk, allowing material to lose energy and spiral inward. Without this mechanism, material would simply orbit indefinitely, unable to fall toward the black hole. The magnetic fields also create chaos. They tangle and twist, building up energy periodically released in flares and eruptions through magnetic reconnection events. The disk is not smooth and orderly, but violent and turbulent, plasma churning under gravity, pressure, and electromagnetic forces. In the innermost regions, within a few astronomical units, conditions become truly extreme. Temperatures exceed billions of degrees, hotter than stellar cores, hotter than anything in nature except perhaps the moments after the Big Bang, or during neutron star collisions. Material moves at 30 to 50% of light speed. Relativistic effects become important. Time dilation, length contraction, frame dragging from the rotating black hole all play roles. This innermost region is the innermost stable circular orbit, the closest distance where matter can orbit without falling in. Its exact radius depends on black hole spin. For a non-rotating black hole, it sits at 3 times the event horizon radius. For a maximally rotating one, much closer at just over 1 event horizon radius. Material here is on the edge of doom. Any slight perturbation sends it spiraling across the event horizon within hours or days. This is where accretion efficiency peaks. Material has fallen through most of the gravitational potential, reached maximum velocities and temperatures, and radiates at maximum rates. This innermost region contributes disproportionately to total luminosity despite occupying small volume. Understanding its physics requires full general relativity and relativistic magnetohydrodynamics, calculations pushing the limits of supercomputers. The total energy output is staggering. Observations across all wavelengths from radio through gamma rays sum to about 4 times 10 to the 40th watts. To put this in context, if you place this quasar at Alpha Centauri's distance of 4.37 light-years, it would appear 10,000 times brighter than our Sun appears from Earth. The radiation would instantly vaporize our oceans, strip away our atmosphere, sterilize all life within hours. Even from the galactic center 26,000 light-years away, it would outshine the full moon, visible in daylight, bright enough to cast shadows. How does this process generate such power? The answer lies in Einstein's E equals mc squared. Mass and energy are equivalent, related by the speed of light squared. The speed of light is enormous, about 300 million meters per second. Squared, this becomes 9 times 10 to the 16th. Even tiny masses contain staggering energy. 1 kilogram converted entirely to energy releases 9 times 10 to the 16th joules, equivalent to 21 megatons of TNT. But most natural processes are far less efficient. Chemical reactions release only about 1/billionth of rest mass energy. Nuclear fission releases about 0.1%. Nuclear fusion, powering stars, converts about 0.7% of mass to energy when 4 hydrogen nuclei fuse into helium. This efficiency lets the sun shine for billions of years, despite converting 4 million tons of mass to energy every second. Black hole accretion is dramatically more efficient. Depending on the black hole's spin, 10 to 40% of infalling matter's rest, mass energy can be radiated before crossing the event horizon. For a non-rotating Schwarzschild black hole, efficiency is about 10%. For a maximally rotating Kerr black hole, it reaches 40% or higher, especially with processes like the Blandford-Znajek mechanism extracting rotational energy from the black hole itself. This extraordinary efficiency arises from extreme conditions near the event horizon. Material spiraling inward falls through intense gravitational fields, losing enormous gravitational potential energy converted first to kinetic energy as material speeds up, then through friction and magnetic interactions to heat, finally radiated as electromagnetic radiation across all wavelengths. The key is that material loses this energy before crossing the horizon. After crossing, it and all remaining energy vanish forever, swallowed by the black hole. Current observations suggest this black hole accretes about 20 to 30 solar masses per year. With 10% efficiency, this produces the observed luminosity. Every year, mass equivalent to 20 or 30 suns crosses the event horizon. Yet despite this voracious appetite, the black hole grows slowly percentage-wise. Gaining 30 solar masses annually when weighing 66 billion represents a fractional increase of less than 1 part in 2 billion. Doubling the mass would take over 2 billion years. This highlights a crucial point about supermassive black holes. They grow slowly relative to their size. Even the most voraciously feeding quasars add only tiny percentages annually. Extreme luminosity comes not from mass increase rate, but from incredible efficiency of converting mass to energy before horizon crossing. How did this black hole become so massive so quickly? This is one of astrophysics' great puzzles. The light we see left, when the universe was only 3.2 billion years old, the Big Bang occurred 13.8 billion years ago, so the universe had existed less than a quarter of its current lifetime. The first stars probably formed 1 to 200 million years after the Big Bang, perhaps earlier. This black hole had at most 3 billion years to grow from a stellar mass seed to 66 billion solar masses. Let us trace the mathematics carefully. Start with a seed black hole of 100 solar masses, perhaps from collapse of one of the first massive population tree stars made of pure hydrogen and helium. This black hole begins accreting from its surroundings, but growth rate is limited by the Eddington limit. The Eddington limit arises because accreting matter heats up and produces radiation. This radiation exerts pressure on infalling matter, pushing it away. If accretion is too rapid and radiation too intense, outward pressure overcomes gravity and blows away infalling material, shutting down accretion. The Eddington limit is not a hard cap on mass, just on growth rate. A black hole accreting at the Eddington limit grows exponentially with an E-folding time of roughly 50 million years. Starting from 100 solar masses, after 50 million years the black hole reaches about 270 solar masses. After 460 million years, about 1 million solar masses. After 920 million years, about 1 billion. After 1.3 billion years, 10 billion. after 1.7 billion years, theoretically 100 billion. So, mathematically, growing a 66 billion solar mass black hole in 3 billion years is possible with continuous Eddington-limited accretion from formation until observation. But this is optimistic. Black holes likely experience periods of active feeding interspersed with fuel shortages. Accretion rates probably vary significantly, sometimes exceeding Eddington during brief super-Eddington episodes, other times falling well below during droughts. There are also fuel supply questions. Growing to 66 billion solar masses requires consuming hundreds of billions of solar masses of gas, even accounting for inefficiency, where only a fraction of mass energy radiates away. That is a significant fraction of an entire galaxy's baryonic matter. Maintaining supply for billions of years is not trivial. Gas must continuously flow into central galactic regions, overcoming angular momentum that tends to keep gas in circular orbits rather than allowing inward fall. Several mechanisms might explain ultramassive black hole formation. First, perhaps they started from unusually massive seeds. Instead of stellar mass seeds of 100 solar masses, maybe they began much larger. In the early universe, before first stars, enormous pristine hydrogen and helium clouds might have collapsed directly into black holes without stellar phases. Direct collapse requires gas not fragment into smaller pieces and not cool efficiently enough to form stars. Theoretical models suggest special circumstances. Perhaps regions where intense ultraviolet radiation from nearby young galaxies prevented effective cooling could produce seed black holes with 10,000 to 100,000 solar masses or more, providing huge head starts. Second, perhaps black holes occasionally accrete faster than Eddington. This might happen if accretion flows are geometrically thick, forming envelopes around black holes rather than thin disks. In such configurations, photons produced internally might be trapped and advected inward before escaping to exert pressure on outer layers. Some models suggest super-Eddington rates reaching 5 to 10 times or higher might be sustainable for limited periods. Third, galaxy mergers play crucial roles. In the early universe, galaxies were smaller and more densely packed. Expansion had not yet carried them as far apart as today. Collisions and mergers were common. When galaxies merge, central black holes eventually merge too, creating larger black holes almost instantly through events releasing more energy in gravitational waves than all observable universe stars emit in light over equivalent time periods. Fourth, the early universe was much gas, richer than today. Star formation had only recently begun, so most baryonic matter was still gaseous hydrogen and helium rather than locked-in stars. This gas-rich environment provided abundant fuel. Perhaps this black hole found itself in exceptionally favorable locations, maybe at protocluster centers where multiple gas-rich galaxies merged, funneling enormous material towards central black holes. The truth probably involves combinations of all these factors. Massive seeds from direct collapse, occasional super-Eddington accretion during intense feeding episodes, multiple mergers with other black holes, and optimal feeding conditions in gas-rich protocluster environments, all working together. But exact details remain uncertain. an active research area with profound implications for understanding structure formation in the early universe. This ultramassive black hole is exceptional but not unique. Across the distant universe, astronomers have found tens of thousands of quasars powered by voraciously feeding supermassive black holes. Interestingly, nearly all are distant, meaning we see them as they existed billions of years ago. In the nearby universe, within a few billion light-years, quasars are rare. Most supermassive black holes, including Sagittarius A star, are essentially dormant, accreting very little and shining far below potential maximum luminosity. This reveals something profound about cosmic history. There was an era roughly 1 to 4 billion years after the Big Bang when quasar activity peaked. At that epoch, corresponding to redshifts Z equals 2 to 3, bright quasars were perhaps 100 times more common than today. This quasar era was a period of intense activity when supermassive black holes grew rapidly and shone brilliantly. Why were quasars more common then? The answer involves fuel availability and galaxy evolution states. Early universe galaxies were still forming and evolving, not yet mature systems, with most gas converted to stars. They were gas-rich, with large baryonic mass fractions still in diffuse hydrogen and helium rather than locked in stars. This provided abundant black hole fuel. Galaxy mergers were also more common. Galaxies were packed closer together and had not yet spread as far apart through expansion. When galaxies collide and merge, interactions efficiently funnel gas towards centers through gravitational torques, stripping angular momentum from clouds, causing rapid inward fall. Results often include starbursts of intense star formation, accompanied by central black hole feeding and quasar ignition. As the universe aged and expanded, conditions changed. Gas was gradually consumed in star formation or expelled by supernovae and stellar winds. Galaxy mergers became less frequent as expansion carried galaxies apart. Most massive galaxies completed assembly and settled into quiescent states. Quasar activity declined dramatically. Critically, energy output from quasars themselves began affecting surroundings through AGN feedback. When supermassive black holes actively accrete and shine as quasars, their radiation heats surrounding gas. Intense ultraviolet and X-ray emission ionizes clouds and raises temperatures. Hot gas has higher pressure and resists gravitational collapse. Heated strongly enough, gas can be blown out entirely in powerful winds, removing fuel for both star formation and further black hole growth. Radiation pressure from quasar light can also drive winds. Photons carry momentum. When interacting with gas, they push it away. For the most luminous quasars, radiation pressure can accelerate gas to thousands of kilometers per second, driving it out of galactic gravitational potential wells. Some quasars produce powerful jets, collimated matter and energy beams shooting from black hole poles at near light speeds. Jets plow through surrounding gas, heating it and creating enormous bubbles pushing gas from central regions. Net AGN feedback effect regulates both star formation and black hole growth. As black holes feed and grow, energy output increases. Eventually, feedback becomes strong enough to disrupt gas supply, shutting down accretion. Quasars fade, black holes stop growing, galaxies settle into quieter states. This self-regulation may explain why the most massive galaxies are not even larger. Without mechanisms shutting down star formation and black hole growth, theoretical models predict massive galaxies would continue growing much larger than observed. We observe this quasar at redshift Z equals 2.219, when the universe was about 3.2 billion years old, right around quasar-era peak. We catch it during glory days when fuel was abundant and feeding voracious. The intense radiation is both product of this feeding and, ironically, probably the beginning of its end. If we could observe this object as it exists today, 10.4 billion years after observed light left, we would probably find something very different. The quasar has almost certainly faded. The black hole may have grown somewhat through continued accretion and possible mergers, but likely no longer shines near peak luminosity. It probably sits dormant at the center of a massive elliptical galaxy, a giant system containing trillions of ancient red stars formed billions of years ago during galactic youth. Gas supplies have long since been exhausted or expelled. The host galaxy has aged and quieted, and the black hole, having consumed everything within reach, entered a quiescent phase, likely lasting the rest of cosmic time. How do we know this black hole's mass? It seems impossible. The object is 10 billion light-years away. We cannot resolve individual orbiting stars as we can for Sagittarius A, where decades of observation revealed stars orbiting with periods allowing precise mass measurements through direct Kepler's laws application. For this distant quasar, we use indirect methods exploiting relationships between observable properties and underlying black hole mass. Remarkably, several independent methods give broadly consistent results, increasing confidence in the 66 billion solar mass estimate. The primary method is reverberation mapping. Quasar brightness varies over time due to accretion flow instabilities and fluctuations. The accretion disk is not smooth and steady, but chaotic and turbulent. When the central disk brightens, nearby gas clouds orbiting the black hole, collectively the broad line region, respond by brightening too. These dense clouds, heated and ionized by intense disk radiation, fluoresce, emitting strong spectral lines, particularly hydrogen Balmer lines. But there is a time delay between disk brightening and broad line region response because light takes time to travel from disk to clouds. By monitoring both continuum emission from the disk and emission line strength from the broad line region over months to years, astronomers measure this light travel time delay. The delay reveals broad line region size. If delay is 100 days, the region extends roughly 100 light days, or about 26 billion kilometers from the black hole. Spectral line widths reveal gas velocity in the broad line region. The Doppler effect shifts light from gas moving toward us to bluer wavelengths and from gas moving away to redder wavelengths. Faster motion creates broader spectral lines smeared by Doppler broadening. With orbital radius from time delay and velocity from line widths, we calculate central mass using gravity laws, the same principle determining sun mass from Earth's orbital properties, but applied to systems billions of times larger and billions of light-years away. For this quasar, direct reverberation mapping is difficult because time delays can be months to years requiring long-term monitoring. However, astronomers developed empirical relationships between quasar luminosity and broad-line region size, calibrated using reverberation mapping of hundreds of other quasars. Using these relationships with single-epoch spectroscopy line-width measurements, astronomers estimate black hole masses without multi-year campaigns. These methods consistently point to approximately 66 billion solar masses. Uncertainties are substantial, perhaps factors of 2 to 3 either direction, meaning true mass could be 20 billion to 200 billion solar masses. But even with large uncertainties, we confidently deal with one of the most massive black holes ever discovered. A completely independent check comes from the Eddington limit. There is a maximum luminosity for any given black hole mass, beyond which radiation pressure blows away infalling matter and shuts down accretion. Eddington luminosity scales directly with mass. More massive black holes have higher Eddington limits. This quasar shines at about 4 times 10 to the 40th watts. For this not to exceed Eddington, the black hole must have mass of at least 30 to 40 billion solar masses, depending on exact accreting material composition and accretion flow geometry. The 66 billion solar mass estimate places the quasar at roughly half to 2/3 Eddington luminosity, meaning very rapid accretion, but not quite at absolute theoretical maximum, a reasonable value consistent with other bright quasar observations. What would approaching this object be like? Let us continue our imaginary journey, pushing closer to observe how the environment changes as we descend into one of the universe's most massive objects' gravity well. We begin several light years out, roughly nearest star distances from our Sunday. The quasar already dominates our view, shining as a brilliant point far brighter than any star or planet. Even at this distance, radiation is dangerous. High-energy X-rays and ultraviolet would deliver lethal doses within hours or days. Radiation shielding would be essential. As we move to 1 light-year distance, quasar apparent brightness increases dramatically, now comparable to sun intensity as seen from Earth, but with far more extreme spectrum, substantial emission in ultraviolet and X-ray regions, instantly destroying unprotected biological tissue. Electronics would malfunction as radiation created spurious signals and damaged semiconductors. Space around us fills with the quasar's radiation field. Photon density is high enough that photons interact with stray atoms. Ultraviolet photons strike hydrogen atoms, knocking electrons free through photoionization. X-rays ionize even tightly bound electrons from heavy elements. The result is a vast bubble of hot ionized plasma surrounding the quasar, heated by intense radiation to millions of degrees, extending for light years in all directions. Moving inward to light months distances, the quasar resolves into extended structure. The point source spreads into a disk. The accretion disk becomes visible as distinct feature, a vast, swirling maelstrom. The disk shows clear structure. Outer regions glow orange and red at tens of thousands of degrees. Middle regions shine yellow and white at hundreds of thousands of degrees. Innermost visible regions blaze blue, white, and violet, approaching millions of degrees. The disk is not smooth, but mottled and clumpy with bright spots and dim regions. These variations reflect local gas overdensities and magnetic field influences. Occasionally, we might see flares, sudden brightenings as magnetic field lines reconnect, releasing stored energy. If this quasar produces jets, we might see them as narrow beams shooting from black hole poles perpendicular to the disk, brilliant searchlights extending thousands or millions of light years. Within light weeks, we are fully immersed in the quasar environment. The disk fills large view fractions. Rotation is perceptible if we watch hours or days. Inner material whips around with orbital periods of weeks or months, while outer material takes years or decades. Differential rotation is visible as inner material overtakes outer, creating spiral patterns and waves propagating through the disk. Radiation intensity is now beyond any human frame of reference. Flux passing through each square meter per second exceeds many stars' total energy output. Photon density is so high that photons interact with each other. At these energies and densities, quantum electrodynamics predicts photon-photon interactions become important. High-energy photon pairs can collide, producing electron-positron pairs, matter and antimatter, from pure energy. These pairs are short-lived, annihilating when meeting and releasing mass energy back to photons. But briefly, we have a sea of particles and antiparticles, constantly created and destroyed, boiling quantum foam of matter and energy. As we push to light days distances, relativistic effects become dramatically apparent. The disk side rotating toward us appears much brighter than the receding side through Doppler beaming or relativistic beaming. This has two components. First, ordinary Doppler effect shifts light from material moving toward us to bluer, higher energies, and from material moving away to redder, lower energies. Second, more importantly at extreme velocities, relativistic beaming. In special relativity, when sources move at significant light speed fractions, emitted radiation beams forward in motion direction. Material moving toward us beams light our direction, appearing much brighter, while material moving away beams light away, appearing dimmer. Combined effect is dramatic. Approaching disk side can appear several times brighter than receding side, even with similar intrinsic emission. Gravitational lensing also becomes important. Light from the disk's far side, which should be hidden behind the black hole, bends around it through extreme space-time curvature. We see a complete emission ring surrounding the black hole silhouette. Light from both near side traveling relatively straight and far side bent around the hole reaches our eyes simultaneously. We see disk above, below, and as a ring around the black hole all at once. At the innermost stable circular orbit where matter can orbit without falling in, conditions are extreme beyond description. Material moves at 10 to 20% of light speed, or possibly faster, for rapidly rotating black holes. Orbital periods might be just hours or days. Material here is on doom's edge. Any slight perturbation sends it spiraling across the event horizon in hours or days. There is no return. Material makes final orbits, radiating away last energy in final X-ray and gamma-ray blazes before plunging past the point of no return and vanishing forever. Now we reach the event horizon itself, the point of no return extending to about 1,300 astronomical units from the center. The circumference measures roughly 8,000 astronomical units around. Light speed travel along this boundary would take nearly 6 weeks for a full circuit. The event horizon is not a physical surface, but a space-time geometry feature, a boundary defined by general relativity mathematics. Below this boundary, space-time warps so severely that all future directed paths point inward toward the singularity. Above, escape is still possible with sufficient velocity. Below, escape is impossible, forbidden by space-time structure itself. Approaching the horizon, looking back toward the outside universe, we see the view dramatically distorted. Light from behind us, from the region we came from, concentrates into increasingly small sky patches directly behind us through gravitational lensing. Looking ahead toward the black hole, we see the shadow, a dark, circular region where no light escapes. Surrounding this shadow is the photon sphere, the glowing ring of accretion disk light bent by gravity to reach our eyes. From our own perspective, nothing special happens at the horizon. We cross at high velocity, perhaps significant light speed fractions if in free fall from large distance. The crossing is uneventful. No physical barrier, no sudden sensation, no local indication anything changed. We simply pass from a region where escape was possible to one where it is not. After crossing, we could still look back and see the universe we left. Light from outside falls inward freely, so we continue receiving external universe images. However, images are increasingly distorted and blue-shifted. If we tried sending signals back, they would never escape, falling inward with us, trapped by the same space-time geometry trapping us. Inside the horizon, we continue falling toward the singularity. The singularity is now in our future as inevitably as tomorrow. We cannot avoid it, slow down, or turn around. According to general relativity, the singularity is not a space place we move toward, but a time moment we approach. Our existence's final moment. As we fall deeper, tidal forces noticeable but survivable at the horizon begin growing. Initially, increases gradual. We feel stretched, pulled more strongly at feet than head, simultaneously compressed horizontally, squeezed from sides. These are tidal forces, differential gravitational effects from space-time curvature. Forces intensify, exponentially approaching the singularity. Discomfort becomes pain, then agony, then overwhelming stress, exceeding biological tissue, breaking strength. Our body tears apart, first macroscopically as bones break and muscles tear, then microscopically as cells disrupt, then molecularly as chemical bonds break. This is spaghettification, the inevitable consequence of falling toward a black hole singularity. For this ultramassive black hole, the journey from horizon to singularity takes many hours, perhaps days of subjective time, much longer than for smaller black holes where journeys might take only seconds or minutes. Longer journey is a consequence of the black hole's size. Larger black holes have gentler curvature near horizons, translating to weaker initial tidal forces and longer time before forces become lethal. But eventually, inevitably, forces become overwhelming. Our body stretches into long, thin strands, then tears apart completely, disintegrated into individual atoms, then subatomic particles. Finally, in last moments, even fundamental particles might be affected as we approach the singularity where space-time curvature becomes infinite. Then we reach the singularity, the end point where all black hole mass concentrates according to classical general relativity. At the singularity, space-time curvature becomes infinite. Density becomes infinite. General relativity equations break down, giving nonsensical answers predicting infinities, suggesting theory incompleteness. This is where current physics understanding fails. We do not know what actually happens at the singularity. General relativity predicts its existence, but cannot describe its properties. A quantum gravity theory uniting quantum mechanics with general relativity is needed. We do not yet have such a theory. Several candidates exist, including string theory and loop quantum gravity, but none has been definitively confirmed. These theories suggest the classical singularity might be replaced by something else. Perhaps a region of high but finite curvature where quantum effects dominate, or perhaps some kind of bounce where collapsing matter rebounds outward, or perhaps something stranger we have not yet imagined. For now, the singularity remains mysterious, a breakdown point of our best gravity theory, a signpost indicating new physics is needed. The existence of this ultramassive black hole carries profound implications beyond mere record-keeping. It is a crucial laboratory for testing physics in extreme conditions and an important probe of cosmic history. Near this black hole, space-time curvature is more extreme than almost anywhere else accessible. While we cannot yet probe innermost regions directly, the accretion disk and broadline region provide indirect general relativity tests in strong gravitational fields. Light bending, gravitational redshifts, frame dragging effects, all these general relativity predictions can be tested through careful observations. So far, all observations are consistent with Einstein's theory, even in extreme conditions, providing powerful confirmation of general relativity validity. The challenge of forming 66 billion solar mass black holes in less than 3 billion years pushes black hole growth theories to limits. Explaining objects like this requires understanding accretion physics deeply, determining mechanisms producing massive seeds, and quantifying galaxy merger roles in assembling ultramassive black holes. These questions have implications beyond this single object, affecting structure formation, understanding throughout cosmic history. Tight correlations between black hole mass and host galaxy properties suggest these systems grow together through intimately linked processes. This quasar, as one of the most massive known black holes at an epoch, when the universe was relatively young, provides a crucial data point understanding this coevolution. How did such massive black holes influence host galaxies through feedback? How did galaxy formation and evolution enable such rapid black hole growth? Answering these questions helps us understand the full story of how galaxies form, grow, and evolve. Quasars like this act as powerful beacons, their light traveling billions of light years, carrying information about the universe it passed through. By analyzing spectra carefully, astronomers identify absorption lines created when light passed through intervening gas clouds. These absorption systems reveal gas distribution and properties in the early universe, providing unique insight into conditions billions of years ago, information obtainable no other way. Is there a maximum black hole size? This ultramassive black hole and its peers approach theoretical limits based on available growth time, Eddington limit accretion rates, and feedback effects potentially shutting down growth. Understanding where these limits lie helps us understand maximum structures gravity can assemble, and feedback roles regulating growth throughout cosmic history. Future space-based detectors, particularly LISA, planned for 2030's launch, will detect supermassive and ultramassive black hole mergers across cosmic history. Detecting mergers of black holes like this would provide entirely new information. Gravitational waves carry information encoded in space-time vibration patterns. From signals, we could determine merging black hole masses with high precision, measure spins, determine orbital parameters, and potentially detect exotic effects electromagnetic observations cannot reveal. Gravitational waves from mergers involving 66 billion solar mass black holes would be detectable across the entire universe with unmistakable signals. Such detections would open completely new windows on the universe. We would observe not electromagnetic radiation, but actual space-time ripples, reality fabric, vibrational modes. This is fundamental, direct gravitational physics detection, providing general relativity tests and potential hints of new physics beyond current theories. While the black hole dominates, it does not exist in isolation. It resides at the center of a host galaxy whose properties remain partially mysterious due to the overwhelming quasar glare. Studying the host galaxy is like trying to photograph a candle next to a searchlight, or measure candlelight beside the sunday. Nevertheless, astronomers have made progress using clever techniques. Far infrared and submillimeter observations, wavelengths where the quasar is less dominant, reveal emission from dust heated by star formation throughout the galaxy. These observations suggest the host is massive, likely containing several hundred billion stars, comparable to or exceeding the Milky Way. The galaxy appears to be undergoing intense star formation, producing new stars at rates perhaps 1,000 times faster than the Milky Way's current rate of 1 to 3 solar masses per year. This vigorous star formation connects to the same gas-rich conditions feeding the central black hole. Both star formation and black hole accretion require abundant gas, and in the early universe, gas was far more plentiful than today. Observations of nearby galaxies reveal tight correlations between central black hole mass and various host galaxy properties, particularly the bulge stellar mass and stellar velocity dispersion. These scaling relations suggest black holes and galaxies co-evolve through linked processes. The correlation is surprisingly tight, with scatter of only about 0.3 dex in the relationship between black hole mass and velocity dispersion. This implies black hole growth and galaxy growth are not independent, but intimately connected through shared gas supplies and feedback mechanisms. For this ultramassive black hole, the scaling relations predict a host galaxy bulge containing roughly 600 to 700 billion solar masses in stars. This would place it among the most massive galaxies in the early universe, a future giant elliptical in the process of formation. The galaxy is probably experiencing a major merger or series of mergers, interactions that simultaneously trigger intense star formation and feed the central black hole. The intense radiation from the quasar profoundly affects its surroundings. This AGN feedback operates through several mechanisms. Radiation pressure from the enormous photon flux can drive winds reaching thousands of kilometers per second. These winds carry away significant gas masses that might otherwise form stars or feed the black hole. Ultraviolet and X-ray radiation ionizes gas throughout the galaxy and even into the surrounding intergalactic medium, heating it to millions of degrees. Hot ionized gas has high pressure and resists gravitational collapse, suppressing star formation. If the quasar produces jets, and many, though not all quasars do, these jets deposit enormous mechanical energy into the surrounding medium. Jets plow through ambient gas, creating shock waves that heat material and create vast bubbles of hot plasma. Radio observations of nearby radio galaxies show these bubbles can reach hundreds of thousands of light-years in diameter, larger than the visible galaxy itself. The energy deposited by jets can prevent cooling flows where gas would otherwise cool and fall toward the galactic center, effectively starving the black hole and shutting down further growth. This feedback is crucial for explaining galaxy properties. Without some mechanism to regulate growth, theoretical models predict massive galaxies would continue forming stars at high rates and grow much larger than observed. The most massive galaxies in the universe today, giant ellipticals containing trillions of stars, are not forming many new stars. They are red and dead. Their stellar populations, dominated by ancient stars formed billions of years ago. AGN feedback provides the regulation needed to shut down star formation in these massive systems. The host galaxy's future evolution is predictable in broad strokes. The intense starburst will exhaust or expel most of the available gas over tens of millions of years. The quasar will fade as its fuel supply diminishes. Star formation will decline dramatically. The galaxy will become dominated by aging stellar populations, gradually reddening as the most massive bluest stars exhaust their fuel and die, while longer-lived red stars continue shining. Billions of years after the epoch we observe, the host will have evolved into a massive elliptical galaxy, a giant system of ancient red stars with little ongoing star formation, the black hole at its center dormant but still massive, a relic from more violent times. The story of how astronomers came to understand this object spans nearly 70 years, a tale of technological advancement, theoretical breakthroughs, and patient observation. In 1957, astronomers at the Tonantzintla Observatory in Mexico were conducting a photographic survey of the northern sky, systematically searching for blue stars. Using special photographic plates and color filters that made blue objects appear brighter relative to red ones, they catalogued thousands of objects. Ton 618 was entry number 618 in the Tonantzintla catalogue, appearing as an ordinary blue point of light. Nothing about its appearance suggested anything unusual. It was simply one more data point among thousands, filed away in archives. The astronomers had no way to know they had captured an image of one of the universe's most massive black holes. The technology and theoretical frameworks needed to recognize its true nature did not yet exist. The breakthrough came in the early 1960s with the quasar revolution. When astronomer Martin Schmidt deciphered the spectrum of 3C273 in 1963, realizing its spectral lines were ordinary hydrogen shifted by enormous redshift, it opened a new window on the universe. Suddenly, astronomers understood that these blue star-like objects were actually extraordinarily distant and luminous, powered by processes beyond anything previously encountered. Over the following decades, astronomers catalogued thousands of quasars. Most seem similar in their basic properties, shining with luminosities of roughly 10 to 100 trillion solar luminosities, powered by black holes containing millions to billions of solar masses. But a few stood out as exceptional, as observational technology improved, particularly with the development of sensitive electronic detectors replacing photographic plates and the construction of larger telescopes. Astronomers could study distant quasars in unprecedented detail. By the 1980s and 90s, advanced spectrographs allowed precise redshift measurements and detailed spectral analysis. For TON 618, these measurements revealed its enormous distance and correspondingly ancient epoch. Its spectrum showed characteristic emission lines from highly ionized species, indicators of intense radiation fields. The lines were extremely broad, suggesting gas moving at tremendous velocities near the central black hole. When astronomers applied reverberation mapping techniques and scaling relations calibrated on other quasars, the results were startling. The black hole mass estimates came back in the tens of billions of solar masses, far exceeding typical quasar black holes. Observations across multiple wavelengths from radio through X-rays confirmed its extreme luminosity. This was not just another quasar, but one of the most extreme objects ever discovered. The recognition of its exceptional nature came gradually rather than through a single eureka moment. Different research groups using different techniques arrived at broadly consistent conclusions. The black hole was ultramassive, among the largest known. The luminosity was extraordinary, making it one of the brightest objects in the observable universe. The existence of such a massive black hole so early in cosmic history posed profound questions about black hole growth and galaxy evolution. Today, astronomers continue studying this object with increasingly sophisticated tools. The James Webb Space Telescope, launched in December 2021, can observe the host galaxy in unprecedented infrared detail, potentially resolving structures and measuring star formation distributions. The Atacama Large Millimeter Array can map molecular gas, the fuel for future star formation and black hole feeding. X-ray observatories can probe the innermost accretion disk regions where relativistic effects are strongest. How do astronomers actually observe something 10 billion light-years away? The techniques are marvels of ingenuity, combining large telescopes, sensitive detectors, and clever analysis methods to extract information from faint, ancient photons. Optical and near-infrared observations use large ground-based telescopes. The Keck telescopes in Hawaii, each with 10-meter diameter mirrors, collect visible and near-infrared light. These mirrors are not single pieces of glass, but segmented designs. 36 hexagonal segments precisely aligned to act as one large mirror. The Very Large Telescope in Chile consists of 4 8.2-meter telescopes that can work independently or combine light through interferometry for higher resolution. The Gran Telescopio Canarias in Spain has a 10.4-meter segmented mirror, currently the world's largest single-aperture optical telescope. These telescopes are equipped with spectrographs that split light into component wavelengths. Modern spectrographs use diffraction gratings, precisely ruled surfaces with thousands of lines per millimeter that spread light into spectra. The spectra are recorded with charge-coupled device detectors, silicon chips where incoming photons free electrons that accumulate in potential wells and are read out electronically. These detectors are extraordinarily sensitive, capable of detecting single photons and achieving quantum efficiencies exceeding 90%. Spectroscopy reveals the quasar's chemical composition, temperature, density, and kinematics. Emission lines identify elements present in the gas. Line widths indicate velocity dispersions. Line ratios constrain ionization states and densities. By comparing observed spectra to theoretical models, astronomers can infer physical conditions in regions they can never directly see. Space-based observations provide complementary data. The Hubble Space Telescope, despite its modest 2.4-meter mirror, operates above Earth's atmosphere, avoiding atmospheric turbulence that blurs ground-based images. Hubble can achieve diffraction-limited resolution and observe ultraviolet wavelengths blocked by atmospheric absorption. For distant quasars, ultraviolet light emitted by hot accretion disk material is redshifted into visible wavelengths observable by Hubble. The James Webb Space Telescope observes primarily in infrared wavelengths from 0.6 to 28 microns. Its 6.5-meter mirror consists of 18 hexagonal beryllium segments coated with gold for high infrared reflectivity. Operating at the second Lagrange point 1.5 million kilometers from Earth, Webb is cooled to about 40 Kelvin by a tennis court-sized sun shield, allowing sensitive infrared observations. For distant quasars, Webb can observe the host galaxy relatively uncontaminated by quasar glare, because at infrared wavelengths, stars emit more relative to the accretion disk. X-ray observations require space-based telescopes because Earth's atmosphere absorbs this high-energy radiation. The Chandra X-ray Observatory uses nested cylindrical mirrors in a grazing incidence configuration to focus incoming photons. These wavelengths do not reflect efficiently at normal incidence, but can be reflected at very shallow angles. So Chandra's mirrors are shaped like nested barrels with radiation grazing their surfaces. The mirrors focus the light onto detectors that record individual photon energies and positions. These observations reveal the hottest material in the accretion disk, gas at billions of degrees, emitting primarily at these extreme wavelengths. Spectroscopy at these energies can detect the signature of relativity in ion emission lines from the inner disk. Ion atoms in the disk absorb and re-emit photons at characteristic energies, but Doppler shifts from orbital motion, and gravitational redshifts from the intense gravitational field spread the line into a characteristic broad asymmetric profile that directly probes conditions near the event horizon. Radio observations use arrays of telescopes working together through interferometry. The Very Large Array in New Mexico consists of 27 radio antennas, each 25 meters in diameter, arranged along 3 arms in a Y configuration. The antennas observe simultaneously, and signals are combined electronically. By correlating signals from different antenna pairs, the array achieves angular resolution equivalent to a single telescope with diameter equal to the maximum antenna separation, up to 36 kilometers. ALMA in Chile operates at millimeter and submillimeter wavelengths shorter than radio, but longer than infrared. It consists of 66 antennas ranging from 7 to 12 meters diameter. ALMA can map cold molecular gas in galaxies, tracing the fuel supply for star formation and black hole feeding. Molecular emission lines like carbon monoxide at characteristic millimeter wavelengths reveal gas distribution, kinematics, temperature, and density. The logistics of observation are complex. Telescope time is precious, allocated through competitive processes. Astronomers write detailed proposals explaining scientific objectives, required observations, and expected results. Peer review committees evaluate proposals and allocate time to the most scientifically valuable projects. Typical oversubscription rates are 3-to-1 or higher, meaning 2/3 of proposals are rejected. Once time is allocated, observations must be carefully planned. Targets must be observable from the telescope location at the time of the observing run. Weather must be considered, particularly for optical and infrared observations requiring clear skies. Calibration observations of standard stars with known properties must be interspersed with science observations. Data rates can be enormous, terabytes per night for sensitive instruments. After observation comes data reduction, converting raw detector outputs into calibrated scientific data. This involves subtracting instrumental signatures, correcting for atmospheric effects, calibrating wavelengths and fluxes against standards, and combining multiple exposures. Specialized software pipelines perform these steps, but often manual intervention is needed for quality control. Finally comes analysis, fitting models to data, extracting physical parameters, and comparing to theoretical predictions. Despite decades of study, fundamental questions about ultramassive black holes like this one remain unanswered. These mysteries drive ongoing research and motivate next-generation observatories. The seed formation question remains controversial. Did these black holes grow from stellar mass seeds of tens to hundreds of solar masses left by the first generation of stars? Or did they form through direct collapse of massive gas clouds into intermediate mass black holes of thousands to hundreds of thousands of solar masses? Or did they grow through hierarchical mergers as smaller black holes combined when their host galaxies merged? Each scenario has theoretical appeal and challenges. Stellar mass seeds are relatively easy to form, but require continuous near-Eddington accretion for billions of years to reach observed masses. Direct collapse seeds provide a head start, but require special conditions that may be rare, particularly suppression of fragmentation and cooling that would normally lead to star formation rather than direct collapse. Merger scenarios naturally explain why the most massive black holes live in the most massive galaxies, but require frequent mergers in the early universe and efficient orbital decay to bring black holes together. Current evidence suggests all three mechanisms probably operate. Some black holes likely grew from stellar mass seeds through steady accretion. Others probably formed through direct collapse in special environments. And many almost certainly experienced major mergers during galaxy collision events. Determining the relative importance of each channel for ultramassive black holes specifically remains an open question. The maximum black hole mass question also lacks a definitive answer. Are there physical limits to black hole growth beyond simply available time and fuel supply? Several theoretical arguments suggest there might be. Radiation pressure from Eddington or super-Eddington accretion can drive powerful winds that remove gas before it reaches the event horizon, self-limiting growth. Feedback heating of the surrounding medium can prevent gas from cooling and flowing inward. Galaxy mergers become less frequent as the universe expands, reducing the supply of fresh gas delivered to central regions. Some theoretical work suggests an upper limit around 100 to 200 billion solar masses, beyond which feedback effects become so strong that further growth is essentially impossible. This ultramassive black hole at 66 billion solar masses approaches these limits, perhaps representing close to the maximum possible mass achievable in the universe. But uncertainties remain large, and the universe may yet surprise us with even larger black holes in yet undiscovered systems. The black hole spin question is also unresolved. Black holes are described by just 3 parameters in general relativity: mass, spin, and electric charge. Electric charge is almost certainly negligible for astrophysical black holes. Mass we can estimate through various techniques. But spin, the black hole's rotation rate, is much harder to measure, yet profoundly important for accretion disk, physics, and energy extraction efficiency. Theoretical expectations suggest black holes should spin rapidly. Accretion naturally spins up black holes, as infalling material carries angular momentum. Prolonged accretion can drive black holes close to maximal spin, where the event horizon rotates at near light speed. However, chaotic accretion from random directions might average to lower net spins. Major mergers can either increase or decrease spin depending on orbital configurations. Determining the spin of distant quasar black holes requires detailed X-ray spectroscopy of iron lines from the inner disk. Observations currently at or beyond the limits of existing instruments. The fate of matter after horizon crossing remains one of physics' deepest mysteries. General relativity predicts all infalling matter reaches the singularity, where space-time curvature becomes infinite and physics breaks down. But quantum mechanics suggests something else must happen. The information paradox, first articulated by Stephen Hawking, notes that quantum mechanics forbids true information loss, yet black hole formation and evaporation seems to destroy information about infalling matter's quantum state. Proposed resolutions include black hole complementarity, where infalling observers experience smooth horizon crossing, while external observers see information encoded in Hawking radiation. Others propose firewalls, where the horizon becomes a region of intense energy destroying infalling matter. Still others suggest modifications to general relativity or quantum mechanics might resolve the paradox. Recent work on black hole quantum entropy and holographic principles suggests information might be preserved, but in ways we do not yet fully understand. These questions are not mere academic curiosities, but windows into fundamental physics. Black holes push our theories to their limits. Understanding them completely will likely require new physics beyond current general relativity and quantum mechanics, a theory of quantum gravity that successfully unites these 2 pillars of 20th century physics. String theory, loop quantum gravity, and other approaches attempt this unification, but none has yet achieved definitive empirical confirmation. The next few decades promise revolutionary advances in observing and understanding black holes. Multiple next-generation facilities currently under construction or planning stages will dramatically improve our capabilities. The extremely large telescope in Chile will have a primary mirror 39 meters in diameter, larger than any existing optical telescope. The mirror will consist of 798 hexagonal segments precisely controlled to act as one. With a collecting area an order of magnitude larger than current facilities, the ELT will detect far fainter objects and achieve much higher spectral resolution. For distant quasars, this means better measurements of black hole masses, more detailed studies of accretion disk structure, and potentially resolved observations of host galaxies. Athena, the Advanced Telescope for High-Energy Astrophysics, is planned as ESA's next major observatory for studying high-energy phenomena. With a collecting area several times larger than current telescopes and improved spectral resolution, Athena will study emission from black hole accretion disks in unprecedented detail. Ion line spectroscopy with Athena could measure black hole spins for dozens or hundreds of systems, testing theories of black hole growth and evolution. The Laser Interferometer space antenna, scheduled for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers. LISA will consist of 3 spacecraft flying in a triangular formation 5 million kilometers apart, using laser interferometry to detect space-time distortions from passing gravitational waves. LISA will be sensitive to gravitational waves with periods of minutes to hours, perfect for detecting supermassive and ultramassive black hole mergers. When 2 black holes, each containing billions of solar masses, spiral together and merge, they produce gravitational wave signals detectable by LISA across the entire observable universe. The signal chirp, rising in frequency and amplitude as the black holes spiral closer, directly encodes the masses, spins, and orbital parameters. LISA observations will reveal the merger history of black holes across cosmic time, test general relativity in strong field dynamical regimes, and potentially discover unexpected phenomena. The synergy between electromagnetic and gravitational wave observations promises particularly exciting science. If a black hole merger produces both gravitational waves detected by LISA and electromagnetic emission from surrounding gas detected by conventional telescopes, multi-messenger observations can reveal aspects of the system impossible to learn from either signal alone. The gravitational wave signal reveals space-time geometry and black hole properties. Electromagnetic emission reveals gas distribution and composition. Together, they provide complete pictures. Theoretical advances will accompany observational progress. Improved computer simulations of black hole accretion increasingly incorporate full general relativistic magnetohydrodynamics, tracking how plasma flows in strongly curved spacetime threaded by magnetic fields. These simulations run on supercomputers using millions of processor hours, solving partial differential equations on 3-dimensional grids with resolution approaching the event horizon. Simulations have already revealed unexpected phenomena like magnetic field reconnection near black holes, turbulence cascades in accretion disks, and jet formation mechanisms. Future simulations with higher resolution and better physics will make increasingly detailed predictions testable through observation. The goal is predictive theory, where simulations can forecast what telescopes should see for different black hole masses, spins, accretion rates, and viewing angles. Machine learning and artificial intelligence increasingly play roles in astronomy, Neural networks can classify objects from survey data, finding unusual systems that merit follow-up. Algorithms can search for patterns in large datasets that human astronomers might miss. Machine learning can optimize observation strategies, deciding which targets to observe and with which instruments for maximum scientific return. These tools amplify human capabilities, allowing astronomers to process data volumes impossible by hand. To understand this ultramassive black hole's significance, we must place it in the broader context of cosmic structure formation, the process by which the universe evolved from a nearly uniform state shortly after the Big Bang to the complex hierarchical structure we observe today. In the beginning, approximately 13.8 billion years ago, the universe emerged from the Big Bang in an extraordinarily hot, dense state. As space expanded and cooled, matter and energy evolved through a series of phase transitions. Quarks combined into protons and neutrons within microseconds. Protons and neutrons fused into light element nuclei within the first few minutes. After about 380,000 years, electrons combined with nuclei to form neutral atoms. The universe became transparent to photons, and the cosmic microwave background was released. But the universe was not perfectly uniform. Quantum fluctuations during the inflationary epoch, when the universe underwent exponential expansion in the first tiny fraction of a second, were stretched to cosmic scales. These fluctuations created regions slightly denser than average, over densities of perhaps 1 part in 100,000. Small perturbations, but crucial. Gravity amplifies density contrasts. Overdense regions attract more matter, growing slowly denser over time. Underdense regions lose matter to their denser neighbors, becoming voids. Over hundreds of millions of years, the overdense regions collapsed, first forming dark matter halos, gravitational potential wells, where dark matter collected. Dark matter, which interacts through gravity but not electromagnetically, collapsed more easily than ordinary baryonic matter because it could not radiate energy and cool. Within these dark matter halos, baryonic matter, mostly hydrogen and helium gas, accumulated. As gas fell into halos, it was compressed and heated. But unlike dark matter, gas could radiate energy through atomic line emission and cooling processes. Radiating energy allowed gas to lose thermal support and collapse further, becoming increasingly dense and eventually forming the first stars. The first stars probably formed 100 to 200 million years after the Big Bang, perhaps earlier. These population 3 stars were made of pure primordial hydrogen and helium, with essentially no heavier elements because no previous stars had lived and died to create metals, as astronomers call elements heavier than helium. Without metals to help cooling, the first stars were probably very massive, hundreds or perhaps thousands of solar masses, burning hot and bright, but living only a few million years before exploding as supernovae or collapsing to form black holes. The first galaxies assembled from these early generations of stars and gas, small, irregular systems, only millions or tens of millions of solar masses, tiny compared to modern galaxies. These proto-galaxies merged and accreted gas, gradually growing larger and more massive. The black holes at their centers, whether formed from collapsed massive stars or direct collapse of gas clouds, also grew through accretion and mergers. By 2 to 3 billion years after the Big Bang, the epoch when we observed this quasar, the universe had reached peak quasar era. Massive galaxies were still assembling through mergers. Gas fractions remained high, providing abundant fuel. Black holes grew rapidly, some reaching billions or even tens of billions of solar masses. This was the universe at its most active and violent, with frequent galaxy mergers, intense starbursts, and brilliant quasars shining across cosmic distances. After this peak, quasar activity declined. Gas was consumed or expelled. Galaxy mergers became less frequent as expansion carried systems farther apart. Massive galaxies completed their assembly and settled into quiescence. Black holes, having consumed available fuel, entered dormant states. By the present day, 13.8 billion years after the Big Bang, most supermassive black holes are essentially starving, accreting at tiny fractions of Eddington rates. This ultramassive black hole represents a particularly extreme outcome of this evolutionary process. Through some combination of massive seeds, optimal feeding conditions, and possibly major mergers, it reached 66 billion solar masses by just 3 billion years after the Big Bang. It sits near the peak of the black hole mass function, among the most extreme examples of what gravity can assemble in the universe. To truly understand what this black hole represents, we must grapple with the nature of space-time itself, particularly in the extreme conditions near the event horizon where Newtonian intuitions completely fail. In everyday experience, space and time seem separate and absolute. Space is the stage where events occur, three-dimensional and unchanging. Time is the steady progression from past to future, ticking forward at the same rate for everyone. These intuitions served physics well for centuries, underlying Newton's mechanics and successfully describing most phenomena encountered in daily life. But Einstein's special and general relativity revealed that these intuitions are approximations valid only at low velocities and weak gravitational fields. Space and time are not separate but unified into a four-dimensional spacetime. The path an object follows through spacetime, its world line, can be tilted different amounts between the space and time directions depending on velocity. This mixing of space and time manifests as time dilation, where moving clocks tick slowly, and length contraction, where moving rulers shrink. General relativity goes further, showing that space-time is not a fixed background, but a dynamic entity that curves in response to mass and energy. Mass tells space-time how to curve. Space-time curvature tells mass how to move. Gravity is not a force pulling objects together, but the tendency of objects to follow straight lines, geodesics, through curved space-time. Near massive compact objects like black holes, space-time curvature becomes extreme. For a non-rotating black hole, the Schwarzschild metric describes the geometry. For rotating black holes, the more complex Kerr metric applies. These metrics reveal startling properties. The event horizon is a null surface, a boundary where the space-time geometry shifts fundamentally. Outside the horizon, time-like world lines can extend to arbitrarily large distances. Inside the horizon, all future-directed time-like world lines terminate at the singularity. Escape becomes geometrically impossible. Inside the horizon, The roles of space and time swap in a precise mathematical sense. The radial coordinate becomes time-like. Just as you cannot stop time's forward progression outside, you cannot stop inward progression toward decreasing radius inside. The singularity at r equals 0 is not a place in space, but a moment in time, the inevitable future for anything inside the horizon. For this ultramassive black hole, the horizon radius of 1,300 astronomical units marks a boundary where space-time curvature, while extreme by everyday standards, is actually relatively gentle compared to stellar mass black holes. Tidal forces at the horizon scale inversely with black hole mass, so ultramassive black holes have surprisingly weak tidal forces at their horizons, weak enough that organisms could potentially survive the crossing itself. The true destructive forces emerge only deep inside during the final plunge toward the singularity. Beyond the physics and astrophysics, this ultramassive black hole invites philosophical reflection on humanity's place in the cosmos and the nature of our quest for understanding. Consider the scale. This black hole contains 66 billion times our sun's mass. The number is so large it loses meaning. Yet, we have measured it. Using instruments and mathematics, human ingenuity has reached across 10 billion light-years and 10 billion years of cosmic time to determine the properties of this object. We have never seen it, except as ancient photons. We will never visit it, but we understand it in deep ways. The black hole does not know we observe it. It does not care about our theories or measurements. It simply exists, governed by physical laws indifferent to our presence. This indifference might seem depressing, suggesting our cosmic insignificance. Yet this indifference does not diminish the value of our quest. The universe does not explain itself. We must figure it out ourselves through painstaking observation, creative theorizing, rigorous testing. The fact that we comprehend black holes represents perhaps our species' greatest achievement. This black hole reminds us that reality is far stranger than everyday experience suggests. Black holes were predicted mathematically before observational evidence, solutions to Einstein's equations that seemed so bizarre, many physicists initially doubted their physical reality. Yet the universe creates them. Nature is not obligated to respect our intuitions. There is also humility in this. We understand much, but not everything. The singularity remains mysterious. Quantum gravity eludes us. Every answer raises new questions. Science never finishes, but continually expands the boundary between known and unknown. This black hole will outlive everything. When all stars die, when galaxies disperse, black holes will remain. They evaporate only through Hawking radiation, an incredibly slow process. For this ultramassive black hole, complete evaporation requires roughly 10 to the 100th power years, a time span so vast the current age of the universe is negligible by comparison. Yet, even this vast persistence ends eventually. Nothing lasts forever. The universe trends inexorably toward maximum entropy, toward thermal equilibrium. The far future is cold, dark, and empty. But we are not there yet. We exist in what might be called the stelliferous era, when stars shine and galaxies sparkle, when complexity and structure fill the cosmos. We use this privileged position to study objects like this ultramassive black hole, pushing our understanding to its limits. This is what makes us human. Not our physical form, but our insatiable curiosity and our determination to understand, even when understanding brings no immediate practical benefit. Beyond the accretion disk itself, many quasars, including potentially this one, launch powerful jets and drive massive outflows that extend the black hole's influence far beyond the immediate vicinity. These phenomena represent some of the most energetic processes in the universe and play crucial roles in galaxy evolution. Jets are narrow beams of matter and energy launched from the polar regions perpendicular to the accretion disk. The exact formation mechanism remains debated, but the leading theory involves magnetic fields threading the disk and black hole ergosphere. As the disk rotates and the black hole spins, magnetic field lines twist and become helical. Plasma flowing along these field lines can be accelerated to speeds approaching light speed, collimated into narrow jets through magnetic focusing. The power source for jets likely involves two mechanisms. First, the Blandford-Payne mechanism extracts rotational energy from the accretion disk. Magnetic field lines anchored in the disk and extending outward act like twisted springs. As the disk rotates, it winds up the fields, storing energy that can be released to accelerate plasma along field lines. Second, the Blandford-Znajek mechanism extracts rotational energy directly from the black hole itself through frame-dragging effects in the ergosphere. A rotating black hole surrounded by magnetic fields can drive electric currents that power jets even without accretion. The relative importance of these mechanisms depends on black hole spin and magnetic field strength. For rapidly rotating black holes with strong fields threading the ergosphere, the Blandford-Znajek process can dominate, potentially tapping enormous energy reserves locked in black hole rotation. A maximally spinning 66 billion solar mass black hole contains rotational energy equivalent to perhaps 10% of its rest mass, an almost incomprehensible amount. Converting even a small fraction of this to jet power could sustain luminous jets for millions of years. Observationally, jets manifest across the electromagnetic spectrum. At radio wavelengths, synchrotron radiation from relativistic electrons spiraling in jet magnetic fields creates extended radio structures. Radio galaxies show jets extending hundreds of thousands, or even millions of light years, from their central black holes, far larger than the visible galaxies themselves. Where jets terminate, plowing into the intergalactic medium, they create enormous lobes of radio, emitting plasma, cavities carved through ambient gas by the jet's ram pressure. At optical and X-ray wavelengths, jets can produce emission through multiple processes. Synchrotron radiation continues into these higher energy bands if electron energies are high enough. Inverse Compton scattering, where relativistic electrons collide with low-energy photons and boost them to higher energies, can produce X-rays and even gamma rays. In some cases, shocked gas, where the jet impacts surrounding material, produces optical emission lines. The speeds achieved by jet material are extraordinary. Observations of radio-bright jets show apparent superluminal motion, features moving across the sky faster than light speed. This is not true faster-than-light motion, but a projection effect, When a jet moves toward us at nearly light speed, the light emitted by features moving along the jet arrives at Earth with progressively shorter time delays, making the features appear to move across the sky faster than their actual velocity. Measuring this apparent superluminal motion allows estimation of true jet velocities and viewing angles. For this ultramassive black hole with its extreme luminosity, outflow effects must be profound. The radiation pressure alone, without invoking jets or mechanical driving, can accelerate gas to escape velocity. The quasar acts like a cosmic fire hose, blasting surrounding material with such intensity that gas cannot remain bound to the galaxy. This self-regulation through feedback is probably why the most massive black holes eventually stop growing despite having enormous gravitational reaches that could in principle draw fuel from vast volumes. The spatial extent of this influence is staggering. Jet lobes can extend millions of light years. Outflows, driven by radiation pressure, affect the entire host galaxy and beyond into the circumgalactic medium. Even in the intergalactic medium, tens of millions of light years away, heavy elements expelled from this galaxy through supernovae and stellar winds mixed with quasar-driven outflows enrich the pristine hydrogen and helium left over from the Big Bang. The black hole's influence reaches far beyond its event horizon, shaping structure on scales millions of times larger than the black hole itself. Understanding how astronomers measure distances to objects like this quasar requires appreciating one of astronomy's great technical achievements. The cosmic distance ladder, a series of overlapping measurement techniques, each calibrated against the previous step. The ladder begins with direct geometric methods. Parallax, essentially triangulation, works for nearby stars. As Earth orbits the Sun, nearby stars appear to shift position relative to more distant background stars. Measuring this angular shift and knowing Earth's orbital diameter allows calculating distance through simple trigonometry. The European Space Agency's Gaia satellite has measured parallaxes for over 1 billion stars, creating a three-dimensional map of our galactic neighborhood. For quasars at such extreme distances, astronomers rely primarily on redshift, the stretching of light by cosmic expansion. For these extreme distances, astronomers rely primarily on redshift, the stretching of light by cosmic expansion. The relationship between redshift and distance follows from cosmological models describing the universe's expansion history. When we observe a distant object's spectrum, we identify characteristic spectral lines from elements like hydrogen, oxygen, carbon, and iron. These lines have precisely known wavelengths measured in laboratory experiments. By comparing the observed wavelengths to the laboratory values, we calculate the redshift parameter Z, defined as the fractional wavelength shift. If a line normally at 500 nanometers is observed at 600 nanometers, the redshift is 0.2. Redshift directly measures the universe's expansion factor between emission and observation. An object at redshift Z equals 2.219, like this quasar, emitted its light when the universe was a factor of 3.219 smaller than today. This is because 1 plus Z equals the ratio of the universe's scale factor now to its scale factor at emission. Converting redshift to distance requires cosmological modeling. The universe's expansion rate changes over time, depending on its contents. Matter, both ordinary and dark, slows expansion through gravitational attraction. Dark energy, the mysterious component causing accelerated expansion discovered in the late 1990s, speeds up expansion. Radiation, important in the early universe, also affects expansion rates. The current standard cosmological model, lambda CDM, specifies these components' densities. About 68% of the universe's total energy density is dark energy. About 27% is dark matter. Only about 5% is ordinary baryonic matter. Radiation contributes negligibly today, though it dominated the early universe. Using these values and solving the Friedmann equations from general relativity, astronomers calculate how light travels through expanding space. For this quasar at redshift 2.219, detailed calculations give multiple distance definitions due to the expansion during light travel. The light travel distance, how far light has traveled, is about 10.37 billion light-years. The co-moving distance, correcting for expansion, is about 18.2 billion light-years. The angular diameter distance, relevant for calculating physical sizes from angular sizes, differs again. These various distances can be confusing, but all follow rigorously from general relativity applied to an expanding universe. The redshift itself is measured to high precision through spectroscopy. Modern spectrographs can measure wavelengths to accuracies of a few angstroms, or better out of thousands of angstroms total, relative precisions of better than 1 part in 1,000. For strong emission lines, this translates to redshift uncertainties of less than 0.001. Multiple emission lines in a single spectrum provide consistency checks. If all lines show the same redshift to within measurement uncertainties, we gain confidence in the value. Systematic uncertainties also require consideration. Gravitational redshift from the black hole's intense gravity could in principle affect lines emitted near the event horizon. But the broad line region, where emission lines originate, sits far enough out that this effect is small, perhaps a few percent. Doppler shifts from gas motion add scatter to individual line measurements, but averaging over many lines reduces this uncertainty. The cosmic distance ladder's power comes from its redundancy. Multiple independent techniques probe overlapping distance ranges. Cepheids and Type Ia supernovae both reach nearby galaxies, allowing cross-calibration. The Hubble constant, describing the current expansion rate, can be measured locally using distance ladder techniques and independently from cosmic microwave background observations. These measurements agree to within a few percent, validating our understanding of cosmic distances. This validation is crucial because the entire distance scale depends on correctly calibrating each rung. Errors propagate. If the absolute luminosities of Cepheids were systematically wrong, distances measured using them would be wrong, throwing off supernovae calibrations, affecting measurements of the Hubble constant, and biasing all cosmological distance estimates. The fact that multiple independent paths through the distance ladder converge on consistent answers provides confidence in the framework. For this quasar 10 billion light-years away, we will never measure its distance through parallax or standard candles. We rely on redshift and cosmology, techniques requiring trust in general relativity and measurements of the universe's composition. But that trust is well earned built on a century of increasingly precise observations converging on a coherent picture of cosmic expansion. While this black hole is exceptional, it is not entirely alone. Astronomers have identified a handful of other ultramassive black holes approaching or possibly exceeding its mass, though uncertainties make definitive rankings difficult. Phoenix A, the central black hole of the Phoenix Cluster galaxy at the center of a massive galaxy cluster, may contain between 40 and 100 billion solar masses, according to various estimates. The large uncertainty reflects the difficulty of measuring black hole masses in such systems. The Phoenix cluster is about 5.7 billion light-years away, much closer than TON 618, existing at a later cosmic epoch. The central galaxy is a massive elliptical, likely formed through many galaxy mergers, and its black hole probably grew through similar processes plus accretion of gas from the hot intracluster medium. S50014 plus 81, a very distant quasar at redshift 3.36, even farther than TON 618, has been estimated at 40 billion solar masses. Its even greater distance and younger cosmic age make its existence particularly puzzling. If confirmed, it would strengthen arguments for massive seed black holes or super-Eddington accretion in the early universe. SDSS J074621, another very distant quasar, has been estimated at potentially 196 billion solar masses, which would make it far more massive than TON 618. However, this extreme estimate has been questioned. The uncertainties are very large, and some astronomers suspect the actual mass may be significantly lower. The challenges of measuring black hole masses for the most distant quasars are severe. What can we learn from this population of ultramassive black holes? First, while rare, they exist in sufficient numbers to rule out TON 618 being a completely unique freak occurrence. Nature has found ways to grow black holes to these extreme masses, likely through combinations of all the mechanisms discussed earlier. Massive seeds, high accretion rates, major mergers, and optimal environmental conditions. Second, the most massive black holes seem to reside in the most massive galaxies, consistent with the scaling relations observed for less extreme systems. The host galaxies are typically giant ellipticals in galaxy clusters, systems that have grown through numerous mergers and have access to large gas reservoirs from the intracluster medium. Third, many of the most massive black holes are observed at high redshifts in the early universe during the quasar era when black hole growth was most vigorous. This supports the picture that ultramassive black holes formed during a special epoch in cosmic history, when conditions were particularly favorable for rapid growth. Fourth, even accounting for uncertainties, there appears to be an upper envelope to the black hole mass distribution. We do not observe black holes of trillions of solar masses. Whether this reflects a true physical limit from feedback effects shutting down growth, or simply the limited time available in the universe's history, or observational selection effects making the most extreme systems harder to detect, remains debated. The population statistics of ultramassive black holes constrain models of black hole formation and growth. Too many ultramassive black holes at high redshift would suggest black hole growth is easier than models predict. perhaps requiring more efficient accretion or more massive seeds. Too few would suggest growth is harder, perhaps requiring special rare conditions. Current observations seem roughly consistent with models, though significant uncertainties remain. Future surveys will discover more ultramassive black holes, refining population statistics. The Vera C. Rubin Observatory's Legacy Survey of Space and Time will image the entire visible sky every few nights for 10 years, creating a time-lapse movie of the universe and discovering countless new quasars. Some will certainly harbor ultramassive black holes. The Euclid Space Mission and Nancy Grace Roman Space Telescope will conduct deep surveys finding the most distant and most massive black holes. Each discovery adds to our understanding of these extreme objects. One of the deepest unsolved problems in theoretical physics concerns the fate of information falling into black holes, a question with profound implications for our understanding of quantum mechanics and general relativity. The problem can be stated simply. In quantum mechanics, information is never truly destroyed. The quantum state of a system evolves deterministically according to the Schrödinger equation. If you know a system's initial state perfectly and track all interactions, you can, in principle, reconstruct the state at any later time. This is called unitarity, a fundamental principle of quantum mechanics. But black holes seem to violate this principle. Imagine dropping an encyclopedia into a black hole. The encyclopedia contains information, the patterns of ink on pages representing knowledge. According to general relativity, the encyclopedia falls through the event horizon and reaches the singularity, taking all its information with it. To an external observer, once the encyclopedia crosses the horizon, all information about its contents seems irretrievably lost. The black hole gains mass but retains no memory of what fell in beyond total mass, charge, and angular momentum. Stephen Hawking complicated the picture further in 1974 by showing that black holes are not entirely black. Quantum effects near the event horizon cause black holes to emit thermal radiation with a characteristic temperature inversely proportional to mass. For stellar mass black holes, this Hawking radiation is incredibly weak, far below detection thresholds. But for tiny quantum black holes, the radiation would be intense. Crucially, Hawking radiation appears to be purely thermal, containing no information about what fell into the black hole. It is like the radiation from a hot stove, characterized only by temperature with no structure encoding information about the fuel being burned. If Hawking was correct, then as black holes evaporate through Hawking radiation over immensely long timescales, the information about everything that ever fell in disappears forever, violating quantum mechanics' unitarity. This is the information paradox. General relativity says information falls into black holes and is lost. Quantum mechanics says information can never be destroyed. Both theories are extraordinarily well tested in their respective domains, but they give contradictory answers about black holes, suggesting at least one theory is incomplete. Recent developments involve concepts like quantum entanglement between particles inside and outside horizons, wormholes connecting black hole interiors to their Hawking radiation, and detailed calculations of how information might be recovered from correlations in outgoing radiation. The field is intensely active, with new proposals and calculations appearing regularly. For this ultramassive black hole, the information paradox is even more dramatic. Over its lifetime, it has consumed hundreds of billions of solar masses of material, each kilogram containing vast amounts of information in the quantum states of its constituent particles. If information is truly lost, this represents an almost incomprehensible amount of destroyed information. If information is preserved somehow, then buried in the extremely weak Hawking radiation this black hole will emit over googles of years, is encoded the complete quantum history of everything that ever fell in, scrambled beyond any practical ability to decode, but theoretically recoverable. The resolution of the information paradox will require new physics, likely a complete theory of quantum gravity, successfully uniting quantum mechanics and general relativity. This remains one of the great outstanding problems in theoretical physics, and black holes, particularly extreme examples like this, ultramassive one, are the key laboratories where our current theories break down and signal the need for new understanding. Our journey ends at the singularity, at the heart of one of the universe's most massive black holes. We have traveled 10 billion light-years from Earth, racing faster than light through intergalactic space, backwards through cosmic time to witness this object as it existed when the universe was young, when galaxies were still forming, when the cosmos was more violent and energetic than today. This is TON 618, home to a black hole containing 66 billion solar masses, shining with 140 trillion suns' light, one of the brightest objects in the observable universe, despite tremendous distance. It is a monument to the universe's capacity for extremes, a gravitational titan from ancient cosmos, a challenge to our understanding of structure, formation, and evolution. It is also a window into cosmic youth, showing us the universe during the quasar era when supermassive black holes grew rapidly and shone brilliantly. It teaches us about black hole formation, galaxy evolution, accretion physics, general relativity in extreme conditions, and the limits of structure formation. The black hole continues to exist, though we see it only as it was 10 billion years ago. Today, in real time, it probably sits quietly at a massive elliptical galaxy center, a sleeping giant surrounded by ancient stars, glory days over. But our study continues and will continue. New telescopes and techniques will reveal more details. Future gravitational wave detectors might observe mergers of ultramassive black holes. Advancing theory will deepen our understanding of quantum gravity and black hole interiors. The story of this black hole is not just about an extreme astrophysical object. It is about human curiosity and determination to understand. It is about the power of science to reveal nature's secrets. It is about our place in a vast universe that does not need us, but which we can nonetheless comprehend. In the far future, trillions of years from now, when all stars have died and galaxies dispersed, black holes will remain, slowly evaporating through Hawking radiation. For this ultramassive black hole, complete evaporation takes perhaps 10 to the 100th power years. Long after every star dies, after galaxies disperse, after even protons might decay, black holes endure. And ultramassive black holes like this will be among the last to disappear, holding out against final darkness for timescales beyond imagination. Yet we can understand it. Using mathematics and physics, we can predict what will happen in that inconceivably distant future. This predictive power is remarkable. We understand processes we will never witness, events separated from us by more years than atoms in our bodies. There is no turning back now. The singularity awaits. This is the end of the journey, the final destination where space-time itself tears apart, where physics as we know it breaks down. Whatever lies beyond our current understanding remains hidden behind the event horizon, perhaps forever beyond our ability to observe. But we keep pushing, keep questioning, keep exploring, because that is what we do. Curious creatures on a small world, reaching out across cosmic distances and cosmic time, seeking to understand the universe we find ourselves in. And in that quest, we find meaning and purpose in an otherwise indifferent cosmos. The journey is complete. The singularity awaits. The story of TON 618 reminds us that the universe is far stranger, far more wonderful, and far more comprehensible than we might have imagined. And that is perhaps the greatest discovery of all.